Hello, welcome all. Welcome to this video. Now we start the discussion of properties of carboxylic acids. Properties can be physical properties as well as chemical properties. We are more concerned with chemical properties or various chemical reactions that carboxylic acid undergo. Before that, a few words on physical properties. Mainly 2 points. One is regarding solubility. Lower carboxylic acids are soluble in water. That can be attributed to the ability to form hydrogen bonds with water. You know, carboxylic acid is highly polar due to the presence of the carbonyl group, which is polar, and OH group, which is also highly polar. So it can have strong dipole-dipole interaction. In addition, due to the presence of OH group, it can have hydrogen bonding as well. Higher carboxylic acids, when this R group become larger, solubility falls. Second point is regarding boiling point. Boiling point of carboxylic acids are found to be much higher than alcohols of comparable molecular mass. And this is again due to hydrogen bonding. In carboxylic acid, there is more extent of hydrogen bonding than in alcohol. You know, in alcohol also there is hydrogen bonding because there is possibility of dimerization if you consider another carboxylic acid molecule written in this way. Okay, so the hydrogen bonding is possible here and also here. Dimerization is possible. So there is stronger hydrogen bonding, and so carboxylic acid has got high boiling point. Now we move on to chemical properties, in which we discuss only one property in this video, that is about acidity of carboxylic acid and also the effect of substituents on acidity. This is a general expression of the dissociation of carboxylic acid, and you know this. You have learned this in chemical equilibria. So carboxylic acid ionize and give carboxylate ion, that is the conjugate base of this acid, and H3O+. The quantitative measure of acidity is given by what is called acid dissociation constant, or Ka, which is the ratio of the concentration of the product, this one, by the reactant. Molar concentration of water is neglected because it's the solvent present in large excess. So the value of Ka indicate the strength of acid. What is the relation? Larger the Ka, stronger the acid. Because if Ka is large, this is to be large, this is to be small, in which case equilibrium is more to the right, then only this will be large and producing more amount of H+ ions. But we know the value of Ka is found to be very, very small, of the order of 10 raised to -5 or -6. Remember, organic acids or carboxylic acids, which are the most acidic functional group compared to alcohol and phenol, still they are considered to be weak acids compared to mineral acids like HCl, HNO3, H2SO4, etc., which are having very high Ka values. But here the value of Ka is found to be very small. So for convenience, for weak acids, Ka is better expressed as pKa, so that you get a very convenient figure, a positive figure. So minus log Ka. This is just like pH, pKw, which are expressed for convenience only. So if Ka is large, pKa will be small because it is negative log. So larger the Ka, smaller the pKa, stronger the acid. So if you have the pKa value, you can easily predict, you can compare acidity based on the pKa value. Okay, keep that in mind. Now, coming to the reason behind acidity of carboxylic acids. You know that when we compare acidity of alcohol, phenol and carboxylic acid, this is the order. Alcohol is least acidic, increases to phenol, increases to carboxylic acids. How do we explain? Why carboxylic acid is most acidic among the three? Now in the lab we can check this using different bases. If you use metallic sodium, which is the strongest base among these three, this is sodium hydroxide and this is sodium bicarbonate, this is weakest among the three. If you put sodium into alcohol, it reacts, displacing hydrogen. And sodium equally react with phenol as well as carboxylic acid. If you use NaOH, alcohol doesn't react because alcohol is not so strong, or it is not so acidic to react with NaOH. But phenol and carboxylic acid react with NaOH, forming their sodium salt, like sodium phenoxide and sodium carboxylate. And if you use sodium bicarbonate, it is still weaker base. We can see that it doesn't react with phenol. Why? Phenol is not so acidic as to react with a weak base, that is bicarbonate. But carboxylic acid react with bicarbonate. It's a very important reaction used in the lab to analyze or detect carboxylic acid. A simple test. What is the reaction? Carboxylic acid react with sodium bicarbonate, forming sodium salt of carboxylic acid, that is RCONA, sodium carboxylate, plus H2O plus CO2. It is the CO2 formation which is the observation, notable observation. Brisk effervescence is produced. This reaction is not occurring with phenol because phenol is not as acidic as carboxylic acid. Okay. Now, what is the explanation? How do we justify this order? Here we have to learn some important generalizations. Okay. Whenever you compare acidity, what you do is you think about the stability of the conjugate base of the acid. This is the conjugate base of this carboxylic acid. Like that, phenol form the conjugate base by losing H plus, it becomes phenoxide. Alcohol become alkoxide. Carboxylic acid become carboxylate ion. All these are anions. So, stabler the conjugate base, stronger the acid. So this is generalization number 1. You have to note this, underline this. I repeat, stabler the conjugate base, stronger the corresponding acid. And it is understandable because if an intermediate is stabler, it is more likely to be formed. Equilibrium is more likely to shift to the right if it is more stable. That's the logic. And this is true for bases also. When you compare basicity of various compounds, you consider the conjugate acid of the base and speak about its stability. Right? So here, when we compare the stability of these conjugate bases, you can see that in the case of alcohol, this R group, that is alkyl group, it has plus psi effect, electron donating inductive effect. Okay, so it is donating electron, so that electron density on oxygen increases. Now this is generalization number 2. You have to note this, another important generalization which is applicable elsewhere in organic chemistry. The point is, for a charged species, this is the negatively charged species anion, any factor which increase the charge destabilize it, and any factor which decrease the charge or diminish the charge stabilize it. This is again a generalization, an important general rule in organic chemistry. I repeat, for a charged species, whether it is positive or negative, any factor which increase the charge destabilize it, and any factor which reduce or diminish the charge or disperse the charge stabilize it. So we consider here these conjugate bases of the corresponding acids. The plus I effect of R increase the charge here, isn't it? So destabilizing it. So this is not that stable. Correspondingly, alcohol is not very acidic. When you come to phenol, you know, in phenol we have an important phenomena. What is this? This phenomena? This is resonance, right? So phenoxide is resonance stabilized, and that make it more acidic than alcohol. If you go to write the next resonance structure, actually you can draw 5 such structures. The next structure is like this, okay, and this will continue. Actually these two bonds are intact, this is displaced, and this continues. You can draw 3 more such structures. Sorry, a correction here. Okay, double bond O, and this lone pair appear here. See, whenever we put a negative charge, remember there is a lone pair, even if it is not explicitly shown. Now this will continue to get more structures. This will shift here, and this pi electron get located on this carbon, and it continues. So you can draw 4, 5 such structures. So this is resonance stabilization in phenoxide that make phenol more acidic than alcohol. Now when you come to carboxylic acid, it's again resonance stabilized, because you can see this lone pair can come to this position, and this pi electron will get displaced here, and you get the next resonance structure or contributing structure as like this. Okay. So this is again resonance stabilized carboxylate ion. So you may ask, then why in both phenoxide and carboxylate ion there is resonance stabilization? Then why this is more acidic? That can be explained in this way. See, in resonance there are some rules which explain the stability of the canonical forms or resonance structures. In carboxylate ion, the 2 structures are equivalent resonance structures. So in that case, resonance stabilization is more. Whereas in phenoxide, if you compare these 2 structures, these are not equivalent, correct? Here negative charge is on oxygen, which is favorable, but here negative charge is on carbon, which is not that favorable. Oxygen is more deserving to hold electron. It can comfortably hold electrons because it's electronegative. And another point, here there is only 1 oxygen to hold this electron density, whereas here there are 2 oxygens to hold excess electron density. So this is more resonance stabilized, correct? So that's about the comparison of acidity of alcohol, phenol as well as carboxylic acids. Right. Now we move on to comparing acidity of aliphatic acids as well as aromatic acids, and how substituents influence acidity. Okay. First we consider aliphatic acids. See, this R is an alkyl group. If another group is connected, a functional group is connected on this R, if it is electron withdrawing, EWG means electron withdrawing group like NO2, Cn, etc. or halogen, what happens? Electron withdrawing groups will withdraw electrons so that the electron density, the negative charge density decreases here. So this becomes more stable. So electron withdrawing groups will increase acidity. Remember that, note that point. See, in aliphatic acids, the major phenomena operating is inductive effect, either minus I effect or plus I effect. And this thing you might have learned in 4th semester itself, this discussion. Now here what? Here a group is connected to this R, which is electron donating group, EDG, electron releasing group like this, alkyl groups, methyl, ethyl, isopropyl, etc. What happens here? When there is an electron donating group, it is pumping electron. So what happens? Electron density over here increases. Any factor which increase the charge, intensify the charge, destabilize it. So stability of this conjugate base decreases. So corresponding acid become weaker. Now we go to examples. pK values are quoted here, and we can compare acidity and we can explain the reason. Look at this. Acetic acid 4.76, chloroacetic acid. So what about chlorine? It is a minus I group, electron withdrawing, it will increase acidity. And you look at the value, pK 2.86. Smaller the pK, stronger the acid. So why this is stronger than this? Because of the minus I effect of Cl. So it will withdraw electron density, okay, and make these OH more polar or more easily ionizable, or you can say that the Cl will withdraw electron and reduce the electron density on oxygen, or you can say in other words, it causes dispersal of the negative charge. Electron density get dispersed. That all make it more stable. Now coming to these two, this one, compare these two, okay. What's the difference here? Here it is fluorine, here is chlorine. You know that fluorine is more electronegative than chlorine. So minus I effect is stronger here. Fluorine more strongly pull electrons. So pK value is smaller here. So this is more acidic than chloroacetic acid because of greater minus I effect of fluorine over chlorine. What about this example? Between these two, what is the point? This is 2.86, this is 1.25, more acidic. Why? Because there are two chlorine atoms, here only one chlorine atom. So more number of minus I groups increase acidity. Coming to this one and these two examples. I did not put the values here anyway. Compare the acidity here, which is more acidic. What is the compound here? This is 3 chloropropanoic acid and 2 chloropropanoic acid. Which is more acidic? Of course this is more acidic. Why? Because here it is only one chlorine in both compounds, but the position of Cl. Here Cl is very close to COH. Here Cl is one bond away. Correct? And you know that inductive effect decreases with distance. So this chlorine has more pronounced minus I effect on this COH, stabilizing this carboxylate. But here Cl is away, so its minus I effect is less than this. So this is the conjugate base of this acid is more stabilized by minus I effect than this. Now compare these two, acetic acid and formic acid, which is more acidic. Formic acid is more acidic because 3.77. How do you explain these two? Here in formic acid it is H connected, here it is methyl group connected. So what? When it is methyl group, you know methyl group has got what effect? Plus I effect. Okay, so plus I effect will donate electron, plus I effect cause electron release, so it will destabilize and reduce acidity. That is not here. That electron donation is not here, so naturally this is more acidic. So when you go to the next one, CH3, CH2COH, that is propanoic acid, it will be still weaker because greater plus I effect. Okay. Now the last example. What about this one? Here you can see a conjugate, a double bond is attached here, and this is a vinyl group. You know, in vinyl this carbon is sp2 hybridized, correct? Whereas in acetic acid this is, or if you take this is sp3. So the difference is, if you compare the two, this is having lower pK, so this is stronger. How do you explain? The carbon connected to COH is sp3 and here it is sp2. So that, you know, sp2 carbon is more electronegative due to greater percentage S character. When S character increases, electronegativity of the orbital increases. So this carbon can withdraw electron more strongly from this group than this sp3 carbon. If you go to, if this is sp carbon, I mean if you take an example, another example, that is CH triple bond COH. Okay, this one, this is propanoic acid. This carbon is sp. It is still more electronegative due to greater percentage S character. sp hybridization means it is 50% S character. So this is still more electronegative and making this still more acidic than this one. So that's all about aliphatic acids. Coming to aromatic acids, here it is only inductive effect which is operating more, and here inductive effect as well as resonance effect will come into play. Generally speaking, as in the case of aliphatic acid, here also electron withdrawing groups may be withdrawing by inductive effect or by resonance effect, like NO2, CN, halogen, etc. That will stabilize this carboxylate. Actually, this is benzoate, isn't it? Ion, and increase acidity. Electron donating group will increase the negative charge and destabilize the conjugate base, and acidity decreases. Groups like CH3, it's due to plus I effect, or it can be hyperconjugation effect. OH and NH2, you know, they have got lone pairs in conjugation with the ring, and they will show what is called plus R effect. Here NO2 and CN can show minus R effect, resonance effect. So electron withdrawing groups increase acidity, and electron donating groups decrease acidity. Let's go to examples. Okay, look at this. This is benzoic acid, 4.2 pK value. When nitro group is coming at different places, this meta, this is para, this is ortho. So it's very important. In aromatic acids, it is not only the nature of the group, but position matters. At which position the group is coming. See, compare the values, 3.5, 3.4, 2.2. What is the nature of NO2? It is electron withdrawing. It will increase acidity. It's correct. pK value has decreased. So these are all more acidic than benzoic acid. Now how do you compare these three? In para position, remember, the resonance effect is predominant when the groups come at ortho and para position, not meta. NO2 group has both minus I effect as well as minus R effect. When it is at meta, it has only minus I effect here, operating here, minus I effect, and acidity increases. When it is at para, it has minus R effect. Okay, but minus I effect is less because the distance is more. NO2 here means it is closer, here means it is farther. So minus I effect is weaker here, but minus R effect is operating. Anyway, these two are more or less having similar acidity. But this is very important, very notable. What is special here? orthonitrobenzoic acid, here acidity is maximum, NO2 is having minus I effect and it is very close to this, so it has minus I effect. But here we understand what is known as ortho effect. This is very notable. Ortho effect. What is it? Ortho substituted benzoic acid, irrespective of the nature of the group, whether it is electron withdrawing or donating, it will always have greater acidity than benzoic acid. You consider this one, benzoic acid 4.2, orthonitrobenzoic acid, that is 2.2, and this one, this is orthotoluic acid. This is called toluic acid because it is CH3, so it's toluene, and carboxylic acid, benzoic acid together called toluic acid, orthotoluic acid. See, this is also more acidic than benzoic acid. That's very interesting. We thought since methyl is electron donating, here it comes here, electron donating, so it may decrease acidity, but actually this is more acidic than benzoic acid. So whatever is the group, whether NO2, CH3 or any group comes in ortho position, acidity is more. So ortho effect is the phenomena by which any ortho substituted benzoic acid is more acidic than benzoic acid itself. Right? What is the reason? There are many interpretations. One possible thing is that due to it is the steric effect which matter here. When ortho substitution there is steric crowding. So what happens is that this COH group remain out of plane. Generally we know in benzoic acid this C double bond O and the aromatic pi electron ring are coplanar, so that there is conjugation. But when a bulky group comes here, this will rotate and remain out of plane, so that the electron release from the ring, this is a kind of plus R effect from the ring, that is prevented. See, generally if you consider aromatic acid, that is benzoic acid, are found to be generally stronger than aliphatic acid. See, benzoic acid is stronger than acetic acid slightly. The reason is, one point is that this carbon is sp2, correct? So there is stronger withdrawal through the sigma bond. Okay. At the same time, this ring electron, the pi electron density can move this direction, a kind of plus R effect. Okay, that is also possible. But this electronegativity of sp2 carbon is predominant and it stabilizes this carboxylate group and it is more acidic. But in ortho effect, when there is a group here, what happens? This carboxylate group remain out of plane, preventing this plus R movement, plus R effect. So this is having this the sp2 carbon has electronegativity, electron withdrawal, and make it more stable, and it is more acidic. So that is called ortho effect. And ortho effect is not just steric factor only, and it is an interplay of many other factors like resonance effect, and also sometimes it is hydrogen bonding. See here, this is called salicylic acid, if it is OH here, and this is salicylate ion. So this is also ortho effect. This is highly acidic, and hydrogen bonding is intramolecular hydrogen bonding is also possible here, and that make it much more acidic, right? So these are various examples, and this is paratoluic acid. What about this? What do you think about between benzoic acid and paratoluic acid, between these two, which is more acidic? This one, why? Because this is an electron donating group and that will decrease acidity, and it is at para position. So this is weaker than this one. This is stronger because of ortho effect. What about this one? See, this one has two effects at the same time. This is a minus I group withdrawing electrons. At the same time, the lone pair can have plus R effect. But I said, when at meta position, plus R or minus R effect will not work. It works only at ortho and para position. So what work here is the minus I effect. That works, of course. Minus I effect will work, and it is more acidic than benzoic acid. Okay, so that's all about acidity of carboxylic acid and the effect of substituents on acidity. We will discuss more examples in the next class, in the live session. Thank you.